So at this point, all three cases have been covered with homogeneous linear higher order differential equations with constant coefficients. So this would be a good time to get into non-homogeneous linear differential equations with constant coefficients. So I've mentioned three general scenarios with these kind of diffie-qs, and the three solutions that could be brought up from those general scenarios. So the first scenario would be real and distinct roots, and in that case the solution would be an exponential function. The second scenario would be repeated roots, and in that case the solution would be an exponential / algebraic function, and the third case would be complex roots. And in that scenario, the solution would be trigonometric. And if you have a mixture of those different kinds of roots, then the solution could be a mixture of all of that. So the first three scenarios for these kinds of diffie-qs, real and distinct, repeated, and complex. So they have solutions that are algebraic, exponential, or trigonometric, or a combination of those kinds of functions. So nothing logarithmic, for example. And in regards to trigonometric, it's just sines and cosines, for the record, no tangents or secants or anything like that. And there's a special technique for solving differential equations of this kind, and it's known as the method of undetermined coefficients. So on the right hand side of the equal sign, this here x squared e to the x, this is algebraic and exponential, and this could be the solution to a homogeneous differential equation if there was a repeated root of -1. So just imagine if the characteristic equation factored to n plus 1 squared. Or I said n plus 1 squared, I meant n plus 1 cubed. If the repeated root factored to n plus 1 cubed, then the solution to that homogeneous differential equation would be x squared e to the x. The reason why this is important is because the annihilator approach allows us to take an nth order differential, non-homogeneous differential equation and transform it into an even higher order homogeneous differential equation. So I've used two terms so far. The first term that I used was the method of undetermined coefficients, and the second term that I just now used was the annihilator approach, and they're fundamentally the same exact technique, and that they work for the same scenarios in differential equations. There is no scenario that you can use undetermined coefficients for that you cannot use the annihilator method for, and they're basically the same thing. Depending on the textbook you read, you might even see them referred to as the same method, or sometimes I've even seen them referred to as two different methods, but they're so similar. As a matter of fact, after you employ the annihilator method, or after you annihilate, essentially, you end up with undetermined coefficients to solve for. So once you get the hang of these different methods, you should be able to use this terminology correctly, whether it's undetermined coefficients, annihilators. You should know which is which, even though they're essentially the same thing. So at this point, you should be well familiar with differentiation as a linear transformation, and the word linear. Linear has an interesting meaning. Like x squared is not linear because, for example, x plus y quantity squared is not the same thing as x squared plus y squared. So squaring a function is not a linear transformation. Sines and cosines, those are nonlinear transformations as well. Sine of x plus y is not the same thing as sine of x plus sine y. Differentiation, on the other hand, is linear. If I said the derivative with respect to x of f of x plus g of x, that's just general Calc 1 knowledge that that's the same thing as saying the derivative with respect to x of f of x plus the derivative with respect to x of g of x. So this is certainly not intended to be a Calc 1 review. Calc 1 is obviously something a few semesters prior to differential equations, but the reason why I'm pointing any of this out is because there is a different way that the derivative of a function can be expressed. Rather than using d dx, we could use the differential operator d. So d dx is essentially the same thing as saying d, differential operator, times f of x. And so for subsequent derivatives, if I wanted to take, say, the second derivative of some function f of x, I could say d squared times f of x. And it's a lot like multiplication when, if I take the derivative of the derivative, I get the second derivative, and that's the same thing as if I said d dx of dy dx, for example, I would get d squared y over dx squared. So multiplication is actually pretty useful in evaluating these differential operators, or just in working with them in general. So I've introduced a new form of nomenclature for a derivative. So instead of saying the derivative with respect to x of f of x, we could say d, or differential operator d, times f of x. And so a differential equation like this, a higher order, or really any order, even a first order for that matter, or whether it's homogeneous or non-homogeneous, anything that's linear with constant coefficients, it can be written in terms of the differential operators. So, for example, y prime prime, that's d squared times y. Now, we're adding 12y prime, so 12y prime, that'd be 12d times y plus 27y. And I have that it's equal to x squared times e to the x. So all this is equal to x squared times e to the power x. And I'm going to actually factor out my y. So in terms of the differential operators, now I have d squared plus 12d plus 27 times y equals x squared e to the x. And if you notice, this is the same exact thing as the characteristic equation that we got when we said that y equals e to some power mx. So instead of having to do that whole setup, we kind of just got lazy here, and we forgot about the letter m, started using the letter d instead. The whole time, characteristic equations, you never really had to do that whole setup to figure out what the characteristic equation of a differential equation was. You could always just eyeball it and figure it out blatantly. So here is everything that I have derived so far with these definitions, with the new differential operator d as the notion for differentiation, and in terms of taking the differential equation and putting it in that notion. So for the past several videos, I've been talking a lot about linear combinations of functions and their derivatives that are equal to 0, and clearly with this new language of differential operators, it's possible to express a linear combination of any function and its derivatives. And so on the left hand side here, I'll circle this in red, this is obviously a linear combination of some function and its derivatives, and it's equal to x squared times e to the power x. Now on the left hand side here, this this linear function of the differential operator d is being applied to our function y of x. And so what you do to one side in solving any equation, you must do to the other. And it might be possible, or in this case, it is possible, that there is a linear function in the differential operator d that can turn x squared times e to the x into 0, because x squared times e to the x is a function that I could take a linear combination of this function and its derivatives and get 0. So if I said f of x is x squared e to the x, the differential operator that would annihilate that, and I mentioned it earlier, would be d minus 1 cubed. And when I apply d minus 1 cubed, let me write that better. So when I apply the differential operator d minus 1 quantity cubed to x squared times e to the x, I get 0. So here's a little bit of some clarification on the claim I made some seconds ago, that the differential operator d minus 1 quantity cubed, when applied to the function x squared e to the x, would be equal to 0. And so when I take d minus 1 quantity cubed, I get d cubed minus 2d squared plus d minus d squared plus 2d minus 1 applied to x squared e to the x, and that's all equal to 0. And I know this right here, this, I'll circle this in blue. This whole thing that I have circled here in blue, let me fix that. This right here would, I know this can all be simplified. So the differential operator d minus 1 cubed, when applied to x squared e to the x, is said to annihilate it, or it's said to be equal to 0. D minus 1 cubed times x squared e to the x is said to be equal to 0. And so that is to say that d cubed minus 3d squared plus 3d minus 1 times x squared e to the x equals 0. And so if I said y prime 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 minus 3y prime prime plus 3y prime minus y equals 0, the solution to that differential equation would be c1 e to the x plus c2 x e to the x plus c3 x squared e to the x. So far at this point, I have explained how to take a linear combination of a function and its derivatives and express it in a different way. And that's what's happened on the left-hand side of the equal sign. So on the right-hand side of the equal sign, I took a linear combination of a function and its derivatives, and I figured out what linear combination of the differential operator would turn the right-hand side equal to 0. And in a nutshell, I figured out what differential equation would the right-hand side of the equal sign satisfy. What homogeneous differential equation would the right-hand side of the equal sign be a solution to? So if I told you that the solution to a differential equation is x squared e to the x, and I wanted to know what differential equation is that the solution to, you could give me a linear combination of you could give me an equation that's a linear combination of some unknown function and its derivatives, and tell me that equation, or that solution satisfies the equation. Now, since linear combinations of functions and their derivatives can be written in differential operator notion, the differential operator can be applied to the right-hand side of the equal sign. So in a nutshell, if I see that on the right-hand side of my equal sign I have something that could be a solution to a differential equation, in essence, I need to figure out what differential equation does that satisfy and multiply both sides of the differential equation by a differential operator that differential equation would represent, to take a non-homogeneous differential equation and turn it into an even higher order homogeneous differential equation. So the differential operator that was found to annihilate x squared e to the x was d minus 1 cubed. So if you had a homogeneous differential equation with constant coefficients and the solution to that differential equation was x squared times e to the x, I'd be willing to bet that when you took your characteristic equation, if that was the method that you employed, at one point or another, you had m minus 1 cubed, or whatever your variable was. So, like solving any kind of equations, what you do to one side, you must do to the other. So, if I multiply everything by the differential operator d minus 1 quantity cubed, I get d minus 1 cubed times this whole madness, d squared plus 12d plus 27 times y, and it's all equal to 0. So I'll box the original equation here in red. This is the original differential equation, and this is a non-homogeneous higher order differential equation with constant coefficients. And this is the end result. This is the new, I guess you could look at it kind of like a characteristic equation. And this is homogeneous. So there's a few takeaways in solving this. It's not so straightforward as just considering all of this equal to 0 and ending up with what it'd be like 5 constants of integration. That will not be what goes on here. So first things first, like solving any of these kinds of differential equations, we need to solve to get the homogeneous part. So the homogeneous part would come from d squared plus 12d plus 27 being equal to 0. So when you get an algebraic equation and you factor it into two things like this, you can always, if so long as you get 0 on the other hand of the equal sign, you can take both of them and set them equal to 0 and solve them as multiple equations. So the same logic would apply with differential equations as well. So here I've got d squared plus 12d plus 27 equals 0. And this is going to yield the homogeneous part. So this is the homogeneous solution and not the particular solution. So to solve this, I'm going to roll with completing the square. So d squared plus 12d plus 36 is equal to 9. I added 9 to both sides. Whatever you do to one side, you must do to the other. So 27 plus 9 is 36, and then 0 plus 9 on the right-hand side of the equal sign, that's just 9. So d squared plus 12d plus 36, that is equal to d plus 6 squared, and that's 9. Let me fix that 2 there. So d plus 6 squared is 9, so d plus 6 equals plus minus 3. So hopefully you can see by evaluation that d would be equal to minus 9 or d would be equal to minus 3. So the homogeneous part of the solution to this differential equation is c1 e to the minus 9x plus c2 e to the minus 3x. All that remains now is the particular solution. So d minus 1 quantity cubed times y equals 0. And this could have all been done in one fell swoop, really. Now, D and M are kind of the same thing in terms of these terms of characteristic equations, or the equations that we get when we apply the differential operators. D and M are, they're basically the same exact friggin' thing, except D is just a differential operator applied to the dependent variable, whereas M is just a scalar multiple in the exponential function. So this would have the same solution as any homogeneous differential equation, where the characteristic equation factors to m minus 1 cubed, and that'd be equal to 0 because it's homogeneous. And if your characteristic equation factors to m minus 1 cubed, hopefully you saw the reduction of order video. So y would be equal to a constant. So instead of saying C1, C2, and C3, I'm going to move on from those constants because I'm talking about the particular solution. In just a few moments, you will see y in particular. So instead of saying C1 or C anything, I'm just going to say A times, let's see, normally it'd be C1 x to the 0 e to the x, but instead I'm going to say A times x to the 0 e to the x. So A times e to the x plus b, and now that'd be b times x to the power of 1 e to the x, so bx e to the x, and my third constant I'm going to say c, so cx squared e to the power x. And I'm going to denote this y sub p. So this is known as a particular solution, and the word particular solution is used a few times in differential equations. I'm not sure why whoever came up with the terminology, they just couldn't maybe come up with something different. Particular solution, we use the word when we're talking about initial conditions. If I said y of 0 equals blah 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 and y prime of 0 equals something else, then we'd refer to that solution as a particular solution. When we're dealing with non-homogeneous differential equations, when we say particular solution, we're talking about a solution that is independent of the homogeneous part of the differential equation. So going back on the two different definitions for the word particular solution, so the term is thrown around heavily. If I had an initial condition, then in solving the particular solution that I would gain from plugging in my initial conditions, I would solve for the C1 and C2 in the homogeneous solution, y sub h, h for homogeneous. In this case, y sub p is the particular solution, and I'm solving for the non-homogeneous solution, for the non-homogeneous part of the differential equation, to gain the particular solution. So in a nutshell, in both scenarios, solving for a particular solution does involve solving for constant coefficients in one way that the term is used. In the one that you'll get before you even run into non-homogeneous differential equations, it involves being given an initial condition and solving for the constant coefficients in your homogeneous part, or in other words, the constants of integration. In the second of the two scenarios, when we're talking about a homogeneous or a non-homogeneous differential equation, the word particular solution involves solving for the constant coefficients, the undetermined coefficients from the non-homogeneous part. So in solving for the constant coefficients A, B, and C, there really is no particular solution or particular, there's no initial condition that we're working with, other than, I guess you could say, the fact that the right hand side of the equal sign is not equal to 0. It's x squared e to the x. So the only way that we'll be able to the only way we'll be able to solve for these constant coefficients is going to be to differentiate and plug it into the equation, and in doing so we will turn a differential equation into an algebraic equation, a lot like the initial setup when we said y equals e to some power m times x, and we would take the derivatives and substitute them into the equation and solve for m. And in that same setup we are going to take a differential equation. We've now come up with a generic solution, and we're going to take derivatives of that generic solution and come up with a particular solution to that. So these derivatives are going to get a little bit hairy to evaluate. So y sub p equals a times e to the x plus bx e to the x plus cx squared e to the x, and so y sub p prime equals a times e to the x plus b, and this is going to be straight up product rule. So the derivative of x e to the x, well, derivative of x is 1 times e to the x, so that would be e to the x plus derivative of x e to the x, so plus x e to the x. It's just straight up product rule right here, plus c, and now I gotta get the derivative of x squared times e to the x. The derivative of x squared e to the x is 2x e to the x plus x squared e to the x. So x squared e to the power x. At this point, from all my independent factors, I'm going to factor out the exponential function e to the power x. So y sub p prime equals a times e to the power x plus b times e to the power x, 1 plus x plus c e to the power x, x squared plus 2x. Let me fix that plus sign there. So y sub p prime equals a e to the x plus b e to the x, x plus 1 plus c e to the x, x plus 2x. And if you notice, in a lot of these cases, or it's x plus, or 1 plus x, or x plus 1 a little bit backwards, but you have something plus its derivative, like x squared plus 2x and x plus 1. That's a pretty common trend in evaluating these problems. So y sub p prime then equals a times e to the x plus b times the derivative of this whole product right here. So e to the x, 1 plus x times e to the x, or e to the x times the derivative of e to the x times 1 plus x, that's e to the x times 1 plus x, plus e to the x times 1 plus x, or times the derivative of 1 plus x, so that's just going to be e to the x. So plus e to the x, because the derivative of 1 plus x is just going to be 1, plus c times the derivative after evaluating with the product rule of that e to the x times x squared plus 2x. The derivative of e to the x is e to the x, multiply that by x squared plus 2x, and you get e to the x times x squared plus 2x, and now take e to the x and multiply it by the derivative of x squared plus 2x, and you get e to the x times 2x plus 2. And so that's the full evaluation of y sub p prime with the product rule. So I've simplified the function y and all of its derivatives in order to substitute them into the differential equation now. So those are all boxed in green. You see y sub p in its simplest form is a e to the x plus bx e to the x plus cx squared e to the x. Y sub p prime equals a e to the x plus b e to the x plus bx e to the x plus cx squared e to the x plus 2cx e to the x. And y sub p prime equals ae to the x plus 2be to the x plus bx e to the x plus cx squared e to the x plus 4cx e to the x plus 2c e to the x. At this point, the particular solution and its subsequent derivatives can be substituted into the differential equation. After setting everything up and prior to combining like terms, this is what I end up with. Do note that I went ahead and multiplied the numbers 12 and 27 by y prime and y respectively. So after combining like terms, what I have boxed here in green is my end result. 40a e to the x plus 14b e to the x plus 40bx e to the x plus 40cx squared e to the x plus 28cx e to the x plus 2c e to the x equals x squared e to the x. Now clearly, I could factor out e to the x on my left-hand side of the equal sign, and from both sides of the equal sign, so from both sides of the equation, e to the x could be divided. So, after factoring out my exponential function and getting rid of it on both sides of my equation, I end up with 40a plus 14b plus 40bx plus 40cx squared plus 28cx plus 2c equals x squared. So, the goal here is to solve for a, b, and c rather than x or y. Do not get that part confused. There's a number of different approaches that could be taken to solving for a, b, and c, but I'm going to go ahead and reduce this to a system of linear equations so I can make all this into a matrix. Now, consider what's being multiplied all by x squared. X squared, so I don't have any quantities in a, so 0a plus 0b it looks like. See, nothing, there's no bx squared, so 0b. But I do have 40c, so plus 40c. And I don't have anything in d, so plus 0d. And that equals 1. So c is clearly 1 over 40. I'll go ahead and say that. Now let's talk about x to the power 1, or just x to the first. There's nothing times a that's being multiplied by x to the first power. There is 40 times b, 40bx. I already circled that. It looks like a 10 now because circle just looks weird, but that is a 40, so 40bx. And then there is the 28c, which I've also circled, and nothing times d. So already I could say 40b plus 28c equals 0, and c is 1 over 40. So I'm not so sure why I've been seeing the letter d, but it's not there. Disregard that. Just forget about this part and this part. But anywho, so 40b plus 28c equals 0. So we've already solved for c and gotten that c is 1 over 40. So b would be minus 7 over 400. So talking about x to the power 0 now. X to the power 0, and we have 40a. So 40a times x to the power 0 plus 14b. 14b, that's being multiplied by x to the power 0. And then 2c. And it equals 0. There's nothing on the other side of the equal sign that is being multiplied by x to the power of 0. So 40a plus 14b plus 2c equals 0. So after plugging in values of b and c to solve for a, I get that a is equal to 39 over 8,000. Ouch. That's a pretty small value there. Actually, my TI-84 had some trouble showing that figure due to formatting. So this has been a relatively lengthy differential equation to solve, and finally we are done. So the final solution to this differential equation is c1 e to the minus 9x plus c2 e to the minus 3x plus 39 over 8,000 e to the x minus 7 over 400 x e to the x plus 1 over 40 x squared e to the x. And you could factor e to the x out of those final three terms if you wanted to. It wouldn't really matter, but this is the final solution to this really lengthy differential equation. So hopefully this has not scared you away from differential equations. The more of these kinds of problems you solve, the more you'll get the hang of it. You'll become better versed at solving these, and these will not seem so tedious once you get more used to them.